Why are you subbing to my mute?
Give me something good.
Why are you subbing to my mute? Why are you subbing to my mute?
Enchanté. Danser. Garçon.
Why are you subbing to my mute?
Enchanté. Danser. Garçon.
Why are you subbing to my mute? 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 Why are you subbing to my mute?
Joker who joined the room.
Why are you subbing to my mute? Well, why are you giving subs to my mute? Why are you subbing to my mute? Why are you subbing to my mute? Why are you subbing to my mute?
Hello, welcome to my kitchen.
Come from all over and they remember us. They go to Long Island, come from Long Island. A couple guys come from Connecticut sometimes. Always good to see you.
Always a pleasure.
Over there, Chi.
But hidden within this immensely bright object is believed to be an ultra-massive black hole. Quasars are thought to be caused by the material that is swirling around a giant black hole. As gas and dust rotates faster and faster outside of the event horizon, within a region called the accretion disk, it heats up, creating massive amounts of energy and forming powerful twin jets of radiation that is being blasted out into space for millions of light years. The light produced by this quasar is so intense that it outshines the entire surrounding galaxy, with an estimated luminosity equal to 140 trillion suns, making it
Why
one
are
of
you
the
subbing to
brightest
my mute?
objects in the known universe. The ultra-massive black hole at the center is currently the largest and most massive black hole ever discovered. This monster contains a colossal 66 billion times more mass than the Sun and has an estimated diameter of 242 billion miles, which is 390 billion kilometers, making it more than 40 times the size of Neptune's orbit. Ton 618
Why are
is
you subbing to
estimated
my
be
mute?
more than 10 billion light-years away in the constellation of Canes Venatici, and the only reason we have detected it is because it is so bright. But although Ton 618 is currently the largest known black hole in the universe, according to scientists, there could be much, much bigger ones out there. In a recent study, it has been suggested that black holes containing more than 100 billion times the mass of the Sun could possibly exist, and they have already been given a nickname: stupendously large black holes. However, whether or not stupendously large black holes can even form in the first place is up for debate, as scientists remain uncertain about how even regular supermassive black holes are born. Like most things in space, there is still a lot to learn about these mysterious dark objects. And although Ton 618 is currently the black hole king of the universe, there may well be another, even larger one waiting to take that top spot.
What are you doing right now? If you're watching this video, chances are you'll be sitting down somewhere. And when you're sat down, you're stationary, right? Wrong. Well, sort of wrong. While you may be stationary on Earth's surface, right now Earth itself is moving, hurtling through space at speeds of around 30 kilometers. per second. Similarly, the Sun is also moving at speeds of around 220 kilometers per second, dragging our entire solar system with it as it orbits the galactic tide of the Milky Way. Of course, we don't feel either of these movements. Gravity keeps us bolted down for the ride. But elsewhere in space, and given enough time, everything moves and everything flows. Nothing remains stationary in space. But what is it that makes the galaxy move? Well, that's going to be our topic today, and it makes for one of astronomy's most intriguing mysteries. As you are watching this video, everything in our local universe for millions of light years, including the Milky Way and the local group, is being dragged through space, pulled through the void towards a gravitational focal point which we cannot see. And whatever it is, it exerts an astonishing, almost godlike influence on the vast swathes of space around it. It is the mystery of the Great Attractor. The Milky Way is a vast, ancient and structured collection of hundreds of billions of stars, known as a galaxy. The universe is teeming with them, many larger and more densely packed with stars than our own. And when this many stars come together, gravity allows them to work as a coherent structure, with a much stronger gravitational influence. Galaxies are so incredibly massive that they can attract one another from millions of light years across space, sometimes getting close enough to collide, producing new, larger galaxies. However, the space between galaxies is significantly more voluminous than the galaxies themselves, and there is another force at work. Space itself is expanding, including the space between galaxies, which pushes them apart faster than they can attract one another, spreading the contents of the universe more sparsely. This is known as the Hubble flow. Galaxies are, for the most part, receding away from all other galaxies uniformly as the universe grows. Consequentially, most galaxies are not close enough to collide with their neighbours. Only very small localized pockets of space, like our local group, will be dense enough to collapse into
Why
a
are you
single
subbing to
structure.
my mute?
However, while they may not be destined to collide, dense concentrations of galaxies can still exert influences on one another, bringing them close enough that the combined gravitational potential of the galaxies attracts more remote galaxies, creating denser concentrations and emptying out the space in between in a self-sustaining process. This forms the overarching structure that stretches across our entire universe, the cosmic web. Kind of like a sponge, there are areas of matter which branch in every direction, and large empty swathes in between. The cosmic web is composed of enormous walls of interacting galaxies, known as galaxy filaments. And these can contain hundreds of thousands of galaxies and span over billions of light years. The galaxies within these filaments migrate through paths within the structure, and streams of interacting galaxies flow, converge and diverge like great cosmic water flows over distances difficult to comprehend. The individual thread-like components of a galaxy filament are known as galaxy clusters and superclusters. Smaller groupings of tens, hundreds or perhaps thousands of galaxies which are more concentrated than the overall density of the filament, and thus have more substantial interactions with one another. In truth, the lines between clusters, superclusters and filaments are slightly fuzzy, primarily because we didn't realise that galaxy structures of filament size could exist when we coined the other terms. We knew galaxies could cluster up, but we never thought that they would be able to interact over billions of light years. How wrong we were. Over the past 40 years, we have managed to build up a comprehensive three-dimensional map of intergalactic space, and we now know a considerable amount about our large-scale surroundings. Not bad for a tiny world existing in the blink of an eye on a galactic timescale. We know that our local group, which contains us, Andromeda, the Triangulum Galaxy, and more than 100 other small satellite dwarf galaxies, is situated in a relatively outlying region to a cluster of more than 1,300 galaxies, known as the Virgo cluster. This cluster happens to be the gravitational core of a much larger colony, containing over 100 galaxy groups like ours, called the Virgo supercluster. One of more than an estimated 10 million galaxy superclusters in the observable universe. The Virgo supercluster extends over an area of more than 110 million light years, and it is thought to be over 7,000 times as massive as the local group, enough to exert a considerable influence on its intergalactic neighbourhood. But the cluster network doesn't end here either. A groundbreaking study in 2014, published by scientists at the University of Hawaii, revealed that the Virgo supercluster is just one component of an even greater network of almost unknowable intricacy and scale. Our home galactic supercluster, Laniakea. The Laniakea supercluster extends over 500 million light-years across space, and is home to more than 100,000 galaxies. It is so vast that, for a long time, we didn't realise that its
Why are you subbing to my
superclusters
mute?
were connected. Laniakea consists of 4 main galaxy superclusters: us and the rest of the Virgo supercluster, the Hydra Centaurus supercluster, the Pavo Indus supercluster, and the Southern supercluster. And despite their enormous cosmic distances from each other, they interlink to create a plethora of flows across space. Because the Laniakea supercluster is so large, it is not dense enough to be gravitationally bound. And so, as the universe expands, instead of coming together and condensing further, it should instead get caught up in the Hubble flow, dispersing the supercluster. But that's not what we are observing in practice, or at least not all of what we're observing. In addition to the universe's expansion elongating the structure, the entirety of the supercluster appears to be being attracted to whatever is in this area. The question is, what could possibly be there that is powerful enough to unite galactic superstructures of this size? Flows of galaxies aren't uncommon within galaxy walls, but this is more than just a flow. There is a gravitational anomaly here with enormous power, which is anchoring the entire cluster together and making it move, like a sinkhole to a 500 million light-year basin. This anomaly is what we mean when we say the Great Attractor. The Great Attractor is the somewhat ominous name given to the gravitational focal point of the Laniakea supercluster, thought to lie somewhere around 250 million light-years away from the Milky Way, and it is attracting the contents of the cluster towards it. Everything for hundreds of millions of light-years is attracted to and flowing towards this one region, which means one of two things. Either there is an unusually high concentration of mass there, like an ultra-massive or dense galaxy cluster, or perhaps something stranger, like a monstrous intergalactic black hole, or a mysterious dark force which is counteracting the universe's expansion. In reality, it is likely to be the product of a dense galaxy supercluster, so massive that it is influencing the entirety of the Virgo supercluster as well as the other clusters around it. But whatever it is, there is one fundamental issue. We can't see it. In addition to the nature of the source itself, one of the main things that makes the Great Attractor mystery so intriguing, yet infuriating, is its location. It lies in an area of the sky which is blocked out by the Milky Way's galactic plane from the point of view of the Earth. Because of where the solar system lies in relation to the Milky Way's galactic plane, its bright illuminated core and dark dusty clouds extinguish the light reaching the galaxy from behind, blocking out approximately 1/5 of our field of view. This area is known as the Zone of Avoidance. where the galaxy's features make it virtually impossible to see or detect anything within or beyond it. There's nothing different about the space behind the zone of avoidance, it is just our position relative to the galactic core that is the problem. In fact, in about 100 million years or so, the Sun will have orbited the galaxy's central black hole, taking us to the other side of the Milky Way where the backdrop of the zone of avoidance will be revealed. But that's going to take a very, very long time, and so for all intents and purposes, we are stuck on this side. And it just so happens that the largest gravitational anomaly in the local universe, which is dragging us and everything around us towards it, happens to lie behind this obstructed region. Ironic, right? It certainly makes for a genuinely interesting and somewhat unnerving mystery in astronomy, which troubled scientists for around 40 years. The first signs of the Great Attractor were detected in the 1970s, when we realised that the Milky Way galaxy is moving through space. Back then, there was no way to see or detect anything behind the zone of avoidance. They didn't have the sophisticated technology that we have at our disposal today. And so, around 40 degrees of the sky remained unmapped and unknowable. However, as scientists began producing the first detailed maps of the cosmic microwave background, that is, the primordial microwave radiation left over from the Big Bang which permeates all of space, they discovered what is known as the CMB dipole, a gradient in the temperature of the sky from one side to the other. Scientists quickly realized that this disparity is the result of the Milky Way moving through space, and the motion in the direction of the red area compresses the oncoming waves of radiation ever so slightly, causing that direction to appear slightly warmer. As we know, galaxies moving through space is not that unusual, as all galaxies are moving apart, largely in accordance with the Hubble flow. But things can affect this flow, namely gravity, and the gravity of objects around a galaxy. The discrepancy between a galaxy's actual movement through space due to gravity when compared with what one would expect in an expanding universe is known as its peculiar velocity. In layman's terms, the speed at which a galaxy moves through space because of something other than the universe's expansion. When we tried to measure our peculiar velocity by tracking the Sun relative to the CMB, we discovered that we are moving towards the constellation of Centaurus at a speed of about 600 kilometers per second. And this isn't by chance either. Something in that area is attracting us, but wherever we were headed, it was situated behind the zone of avoidance. And so the cause of this peculiar velocity remained a topic of fierce debate and speculation for many years. Initial hypotheses were that there were just simply more galaxies in the direction of the zone of avoidance, which we just couldn't see. The Milky Way's outlying position to the much denser Virgo cluster was also attributed as a possible cause. However, while the Virgo cluster could attract us with its gravity, it is not nearly massive enough to explain the speed at which we are moving. Something considerably more massive was to blame. And then the mystery got even bigger, quite literally. As redshift surveys began mapping the universe in 3D during the 1980s, we realised that not only are we moving towards this gravitational anomaly in Centaurus, but so are the galaxies both above and below the zone of avoidance. The power of the source was much greater than once thought. In 1986, it was estimated that the source of this anomaly lies between 150 million and 220 million light-years away, and 2 years later, an international team of researchers, led by Donald Lyndon Bell, proposed that the observed motions of 400 elliptical galaxies were best fitted by a large bulk flow of galaxies towards a so-called Great Attractor, lurking behind the zone of avoidance. And thus the term was coined. While we didn't know what was causing the Great Attractor, in order to explain our peculiar velocity, as well as the motions of so many galaxies around us, the source of the Great Attractor was predicted to be around 10 quintillion times the mass of the Sun. That's 10 million billion suns, equivalent to many thousands of massive galaxies. And so naturally, astronomers were keen to establish exactly what was lurking in the dark. Back when it was first noted, our search for the Great Attractor was severely hindered by the zone of avoidance. But times have changed and technology has vastly improved. For one thing, we're not simply limited to observing visible light anymore. While the Milky Way's plane might be opaque to light that we can see, radio and infrared emissions from galaxy superclusters outside of the Milky Way are capable of penetrating the galaxy's clouds, even if only slightly. This gives us some idea of what could lie beyond the avoidance zone, albeit a very limited picture. Instead, the best means we have of seeing behind the zone of avoidance is through X-rays. X-rays are another kind of electromagnetic radiation, like visible light, radio and infrared. Like the latter, X-rays can also pass through the opaque galactic plane and are emitted by galaxy superclusters. In addition, there are far fewer X-ray emitting sources in space than there are sources of infrared and radio waves, making supercluster X-ray emitters easier to identify. In 1996, using data from the Rosat microwave mission, a team of researchers, led by South African astrophysicist René Kraan-Korteweg, discovered evidence for a galaxy supercluster within the zone of avoidance that had previously evaded detection, now thought to be a key galactic concentration at the heart of the Great Attractor. While the cluster had been undetectable through visible light within an area spanning just 2 degrees of the sky, by plotting the X-ray sources identified by Rosat onto the area, a significant galaxy cluster is revealed in the backdrop, known as Arbel 3627, also known as the Norma cluster. The Norma cluster lies around 220 million light-years away from the Earth and is thought to be very close to the proposed heart of the Great Attractor. And it is thought to have a mass in the region of 1 quadrillion times that of our Sun. And so, we realised that the Great Attractor was probably a supercluster with Arbel 3627 near its core. However, even at the time, the team knew that the Norma cluster probably didn't account for the full picture. While it is massive, it didn't seem massive enough to account for the peculiar velocity of the Milky Way. Something else must be at work. But unfortunately, we were still limited in what we could observe due to the obscured zone, and so the mystery remained inconclusive heading into the new millennium. While many scientists agree that the Great Attractor is the result of a dense galaxy concentration, I should take this opportunity to mention that it is by no means the only theory. There were those who refuted the idea of a galaxy supercluster being responsible due to the incomparable scale of its influence when compared with other cosmic structures. In fact, because the universe's expansion is thought to be powered and accelerated by a phenomenon known as dark energy, there are those who suggest that only something equally as dark would be sufficient to overcome it. Dark in the sense that it is unknown and beyond our realm of understanding. This brings us onto a branch of alternate explanations for the Great Attractor. The idea that instead of a galaxy supercluster attracting us, a mysterious, undiscovered force is responsible for the bulk flows of galaxies that we see in Lanikia, like enormous jet stream air currents in the vacuum of space. This idea is called dark flow, and it is defined as a non-random component of the universe's expansion which deviates from the Hubble flow, causing galaxies to stream towards a single point like the Great Attractor, rather than receding away from one another as one might expect.
Why
If
are
this
you
is the
subbing to
case,
my
and
mute?
there is something darker at play than we yet realise, then perhaps we might be able to see evidence of a gigantic flow mechanism by searching for something at the opposite end of the Great Attractor. A great repeller, if you would. While that might sound a bit outlandish, in 2017 we did see something just like this. The dipole repeller. Just as all galaxies in the Laniakea supercluster are flowing towards the Great Attractor, they all seem to be flowing away from an area on the opposite end of the supercluster, a region which appears to be pushing its galaxies outwards and setting them on their galactic paths towards the Great Attractor. Perhaps the Great Attractor and the Dipole Repeller are part of some dark cosmic system capable of overcoming the effects of the universe's expansion. However, while the Dipole Repeller may seem anomalous and indicative of something more spooky, dark flow certainly doesn't need to exist to explain it. In fact, the Dipole Repeller probably isn't even an anomaly, but rather a natural byproduct of galaxy cluster formation. As the compound process of galaxies gathering and attracting more galaxies creates denser galaxy clusters, this process in turn empties out the space around the cluster, creating voids between clumps of galaxies. The more populous and massive the galaxy cluster, the more voids will form around it, as areas are raided for their galaxies to feed the structure. And so, while it may seem like galaxies are being pushed away from the Dipole Repeller, in reality nothing is pushing them, only the pulling force of gravity. And the Dipole Repeller is merely just an area which has had its galaxies emptied out by massive influences, which holds the appearance of a so-called virtual repeller. So then, if there is no dark force at work to produce these flows, then what is causing us to move so fast, if not the clusters in the region of the Great Attractor? In the early 2000s, a study called the Clusters in the Zone of Avoidance Project, or CESA, selected X-ray signatures recorded by the ROSAT mission for follow-up and investigation with newer, more effective X-ray technology. The aim of the project was to map this final portion of the sky in the zone of avoidance that remained uncharted for so many years, and also to focus in on what makes the region of the Great Attractor so great. In doing so, they identified over 200 previously undiscovered galaxy clusters in galactic no man's land, including in the proposed region of the Great Attractor. However, these clusters were found to be significantly less massive than what was once predicted to account for our peculiar velocity, only a tenth of the proposed mass, in fact. In reality, the Great Attractor is not nearly as great as we once thought. While it is the focal point of the Laniakea supercluster which is dragging us towards it, it is not the only thing influencing us. Instead, the CESA survey revealed a substantial concentration of galaxies much further beyond the Great Attractor, near the Shapley supercluster. The Shapley supercluster is one of the most studied of its kind, with its 25 constituent galaxy clusters marked here in blue. It is situated around 650 million light-years away from the Milky Way, and while it was discovered in the 1930s by Harlow Shapley, it didn't become a topic of interest until the late 90s and the advent of better technology. But from 1997 until 2001, no less than 40 scientific papers were published on the cluster, and in 2005, CESA discovered a concentrated region of galaxies in the vicinity of the Shapley supercluster, nicknamed the Shapley Attractor, an even greater and more massive galactic overdensity than the Great Attractor, lying around 500 million light-years away. In total, Shapley is home to more than 8,000 galaxies, and has a mass equivalent to about 10,000 times that of the Milky Way, 4 times greater than the mass observed in the region of the Great Attractor by the same project, and so it is now believed that this supercluster is contributing the lion's share of influence responsible for the Milky Way's peculiar velocity. While everything in our supercluster is flowing towards the Great Attractor itself is being pulled towards the Shapley supercluster. Yes, the reason that the Milky Way is being pulled so quickly towards Centaurus is due to the fact that it is not just the Great Attractor attracting us in that direction. Our peculiar velocity is likely the result of a compound effect, with the Great Attractor responsible for about 44% of the motion being closer to us, and the remaining 56% of our velocity owes to the much more massive and remote Shapley supercluster. which is dragging the Great Attractor and thus the galaxies in our supercluster along with it. And so it was with this crucial piece of the puzzle that astronomers at Hawaii University were able to redefine the boundaries of our local supercluster using the Great Attractor and the effects of the more remote Shapley Attractor to map our galactic colony and define the Laniakea supercluster. But there was one more piece of the mystery which we had yet to discover. When the Shapley Attractor was identified, astronomers speculated that there may be another, even more remote galaxy supercluster which is also contributing to our perceived movement across space. And, only 5 years ago, did Renee Kran-Korteweg and her team, the same team that discovered the Norma cluster some 20 years prior, finally solve the mystery that they had been studying for many decades. In 2016, Kran-Korteweg and her team announced the discovery of a new supercluster in the zone of avoidance region, even further beyond than the Shapley supercluster. Using data from the Anglo-Australian Telescope and the Southern African Large Telescope, they identified a region of overdensity consistent with a galactic supercluster around 800 million light-years away. This galaxy cluster, termed the Vela supercluster, is the final piece of the puzzle, thought to contribute at least 50 kilometers a second to our peculiar velocity. With the influence of the Norma cluster, the Shapley Attractor, and a little help from the Vela supercluster, the observed effects of the Great Attractor that were noticed all those years ago can finally be explained. So with all these things considered, what will be the outcome for us? Will we be pulled into the centre of the Great Attractor? Will the rest of the Laniakea supercluster? Will it destroy our galaxy in the process? Well, the answer is almost certainly no. While we are being lugged in the direction of these superclusters against the expansion of the universe, the force that drives the Hubble flow is accelerating. We will never reach the Shapley supercluster, or even the Great Attractor for that matter, as before long, dark energy will have inflated the universe so aggressively that the influences of the Great and Shapley Attractors will no longer be able to overcome it. Though we are moving towards Centaurus right now, the only thing we are headed for is a collision with Andromeda and anything else which remains in the local group. Our only eventual destination is the void. The Great Attractor, like all galaxy clusters and groups, will be dispersed into its constituent galaxies, each being cast into its own section of space thanks to the force that drives the universe's inflation. But hey, right now the separation of galaxies hasn't occurred yet, and it's going to be a pretty long time before it does. And we are fortunate enough to exist at a time when we can observe brilliant cosmic structures like Laniakea without them vanishing over the cosmic horizon. There's just something about galaxies flowing like great lakes across space that seems tantalizing and beautiful, and it is remarkable just how far gravity propagates. And though the Great Attractor was a gravitational mystery for many years, the biggest unsolved mystery is gravity itself.
Why are you subbing to my mute?
Astronomers have begun one of the most far-reaching efforts. The science of cosmology, the study of the universe as a whole. They are mapping the positions of galaxies across the sky and extending deep into the universe.
So that was only at the end.
Their goal?
Can you show us something?
To link the evolution of
how it was
planets,
looking when it was good.
stars, and galaxies,
Clearly something out
the
there with
universe
this
we
guy.
see around us, with conditions that existed at the dawn of time. What forces came together to form the very first generation of stars and galaxies? And over time, the vast architecture of matter and light we see in our telescopes.
I need a little patience,
Only
a little separation for my health. I'm really good at waiting,
giant rotating disk of
but
stars,
lately I've been
dust,
waiting
and
by
gas.
myself. It sounded good on paper, but that's the reason why I had to leave, surrounded by this vapor. I thought it was the air that's hard to breathe. Whoa,
Now know that our
I guess I found a reason, guess I found a reason. Whoa,
dwarf
I guess I found a reason, guess I found a reason. I guess I found a reason, guess I found a reason. Whoa, I guess I found a reason, guess I found a reason. It probably wasn't worth it. I never knew it'd be the hardest part. But how was I to know that when everything was working at the start? I still remember dancing, but you would always dance 2 steps ahead. They always mention falling. I didn't know I'd fall right through your hands. Whoa, I guess I found a reason, guess I found a reason. Whoa, I guess I found a reason, guess I found a reason. I guess I found a reason, guess I found a reason. Whoa, I guess I found a reason, guess I found a reason.
Why are you giving subs to my mute? Why are you subbing to my mute? You're being fucking jealous, and it's cringe.
Every rooftop talk, every stolen kiss, every late night walk, every secret wish, every second chance, every time we dance underneath the light of street lamp.
Won't you come over? Dying to know where you came from. We're breaking open.
You're being fucking jealous, and it's cringe. Why are you subbing to my mute? Why are you subbing to my mute? you're being fucking jealous, and it's cringe. Why are you subbing to my mute?